month ago, we had a lot of people that weren't doing well in this class, but you guys have put in some good work and brought grades up. So there's a few people still need to get a little work done, but for the most part, we're looking a whole lot better than we were. So kudos to you guys. So, all right. So, good thing. Let's see. The semester final is coming up. Our semester final is going to be Wednesday, December 18th. So that's 9 days from now. Our final is at noon. Exactly 12 o'clock. So our final's earlier than our usual class. I'll remind you again next week. But our final will be Wednesday, December 18th at 12 o'clock. Not 12:45, not 12:49. 12 o'clock is when our final is. And you'll have an hour and 55 minutes because the final runs from noon until 1:55 for third period. Then if you have a fourth period, it'll follow 5 minutes later at 2 o'clock, 2 to 3:55. But yeah, the first day, there's 4 finals on the Wednesday, 0A, first, third, and fourth. And there's 3 periods on Thursday and 3 finals on Thursday and then 2 on Friday. So 4 finals, 3 finals, 2 finals. So whatever your schedule looks like, I do have this posted in Google Classroom. So you can look in Google Classroom to see your final schedule. But Algebra 2 is a required final. You cannot exempt from this class. Hopefully you can exempt from some of your classes by not having too many absences, missing assignments, all that kind of good stuff. So make sure you're checking out those exemption requirements for those classes that you can exempt. But again, alas, we cannot exempt Algebra 2. That's a required final. So, but yeah, like I was saying, a lot of people have brought their grades up. We don't have nearly as many people in jeopardy of failing as we did a month ago. A month ago, we had quite a few people that mainly was just missing work. It's not that, you folks, when you turn in stuff, you're failing all your assignments. That's not usually the case. Most of the time, you're not turning in things, and it's the zeros that are bringing your grades down. But it is what it is. All right, let's take a look at what we have this week. I'm kind of interested myself. I haven't looked at it today. I looked at it on Friday, so I know what we're doing. But I've slept since then. Had a weekend. Let's go to our grade screen. As usual, we'll scroll all the way down here. We've got 4.05 polynomial identities and proofs. Proofs. You thought that was gone after geometry, didn't you? And we have solving polynomials discussion-based assessment. All right, we had one of those earlier in the semester. We have another one this week. So those are both this week. And then we have the fall semester exam next Wednesday. 4.05, 4.07. Let's go take a look at what it has in Buzz for those 2 assignments. Polynomial identities and proofs lesson. A lone wolf howls in the distance as crickets chirp near the lit windows of a decrepit mansion. Inside, someone has eaten the last slice of pizza. And it is Professor Sherlock McMurlock's job to find out who. Was it Mr. Abbott with the sauce stain on his white vest? Maybe it was Mr. Salinas. He did say he was still incredibly hungry. Of course, no one would suspect polite Ms. Weber. To find the offending pizza nabber, McMurlock will have to follow the clues. Well, the same logical process is used when developing mathematical proofs, right? Mathematical proofs are typically introduced in geometry, though the skill and the reasoning used is developed throughout all math courses. So let's solve some mini math mysteries because there's lots of proofs that don't involve triangles. So we're going to learn how can polynomial identities be proven and what can polynomial identities apply to beyond just polynomials. So let's read these identities that have already been utilized. We've already looked at this. The difference of squares. right? Where if you have x squared minus y squared, you can factor that to x minus y, x plus y. One of those cheat codes. Square of a binomial. If you have x plus y squared, we learn there's a pattern that we can do to multiply those together, because that's x plus y times x plus y. It's x squared plus 2xy plus y squared. And additionally, if it's a minus, it's exactly the same except for the middle term now has a minus. X squared minus 2xy plus y squared. So those things we've learned. Those are other identities. Difference of cubes. If we have x to the third minus y to the third, we learn that we can factor that using this cheat code. You take x minus y, since this is an x minus y to the third, x minus y times x squared plus xy plus y squared. These are all positives. So that's a cheat code. And then there's the sum of cubes. This was the difference of cubes. The sum of cubes looks very similar, except for now this has a positive sign and this has a negative sign. See, they look very much the same. This one here had a negative sign and a positive sign when it was a difference. But now that it's a sum, we add here and subtract here. So these are all identities that someone has proved originally. We didn't accept those in math until somebody wrote a proof. And sometimes proofs are hundreds of pages long. We're not going to look at any of those. To prove something, it's important to look at all the clues. Some clues will lead to the goal, others lead to dead ends. Proof is very much trial and error. Let's take a look at proving the difference of squares. So we had x squared minus y squared, and we said that's the same as x minus y and x plus y multiplied together. That's the two factors. It's what we know to be true, but is it? We really had to prove that. So we can start here with the two factors, x minus y and x plus y. So what could the next step be? Let's see. X squared minus y squared. The x multiplies by the other x, and the negative y by the other y. Let's see what do we have here. X squared minus xy minus y. Let's see if I click on that. Not quite there yet, right? That's what the end product we're looking for, but not quite there. Got to use the distributive property. Follow a different clue. Well, there's this clue. The x multiplies by the other x, and then it multiplies by the y, and then the negative y multiplies by the other y. Well, see, I don't think we're hitting all the clues, right? It's close, but that's not fully the distributive property because we only multiplied this by the y. We didn't multiply it by the x also. So if you go to x squared plus xy minus xy minus y squared, where you multiply the x by both of these other terms, and then you multiply the negative y by both of these other terms. Excellent detective work. So the distributive property allows each term to multiply by the other terms. So there's only one step to go. When we have this, we end up with this because the middle two terms cancel each other out. So the middle terms cancel out, and just like that, the difference of squares identity has been proven to be true just by working backwards. Once an identity is proven, then we can apply that to different scenarios. So this is called an algebraic proof because algebra was used to prove it. Makes sense. So having these kind of skills will hone your math detective skills. I don't know if it's going to help you figure out who ate the last slice of pizza, but at least we can do the math. So here's an example. Prove that the identity, the square of a binomial, is true. And we said that if you have x plus y squared, that's the same as x squared plus 2xy plus y squared. So where would we start? So we can start with this, the unsimplified side, the x plus y squared. And that leads us to x plus y. We can rewrite that. Then with this, we can use the distributive property, right? Distributive property, and that will result in x squared plus xy plus xy plus y squared. We're really close. All we have to do now is simplify that because we got xy plus xy. Adding those middle terms together that are the same, xy plus xy results in 2xy. And that's exactly what we were looking for on the other side. Way to go, detective. Wonderful. Let's go to page 2. All right, we have a video where we're looking at the sum of cubes, a to the third plus b to the third.
Hello, today we're going to talk about algebraic identities. Here you'll see the sum of cubes, and I'm going to prove to you that the sum of cube works. So, the first problem we're going to do is 2 cubed plus 3 cubed, and you're probably wondering, well, I can go ahead and just cube each one and add them, which you can, but I'm going to show you using the proof. So the first thing I want you to do with the sum of cubes is identify your a and your b. In this case, my a is a 2 and my b is a 3. So I'm going to plug these values into the sum of cubes. This is going to give me 2 plus 3, 2 squared minus 2 times 3 plus the 3 squared. Now I'm going to use order of operations to simplify. I have 2 plus 3, which is 5. I have 2 squared, which is 4, minus 2 times 3, which is 6, plus 3 squared, which is 9. I still need to finish simplifying inside my parentheses here. So I have 4 minus 6, which in this case is negative 2, and negative 2 plus 9 is 7. And then I have 5 times 7, which is 35. So if we go back to our original problem over here and we solve it just using order of operations, if I cube my 2, that would give me an 8. And if I cube the 3, that would give me 27, which if I add these two, give me 35. So as you can see, the sum of cube does work. So let me show you, now that we have a binomial here, how you can use the sum of cubes to get your answer. Remember, you always want to identify your a and your b. So in this case, my a is the cube root of 8, which is 2x, and the cube root of 27, which in this case is 3. So I'm going to plug these values right into my formula. So I'm going to get 2x plus 3, and then I'm going to get 2x all squared minus 2x times 3 plus 3 squared. And we're going to go ahead and simplify. First parentheses is just going to be 2x plus the 3. In the second parentheses, remember that we're taking 2x and squaring the whole thing. So this is actually going to be 4x squared. Then we have minus 6x because we multiplied the 2 and the 3, and then plus 9. And this here is our final answer. And that's how we use algebraic identities.
There we go. Proving identities. I like the way you have the 2 to the third plus 3 to the third, that we can plug that in and show that it actually does work. So using identities to describe numerical relationships. So when looking for proof of the identity of the pizza nabber, Professor McMurlock had to take his clues and apply them to the other facts that he knew. Similarly, polynomial identities go beyond just expressions with variables. They can be applied to numbers, both real numbers and imaginary numbers. Remember, we see complex, think imaginary. And even up to trigonometry, sine, cosine, all that good stuff. Earlier, the difference of squares was pretty true. So observe as it will be applied to a numerical relationship. So if we were given the problem 36 minus 9, we can look at that and say those are both squares. 36 is a perfect square. It's 6 squared. 9 is a perfect square. That's 3 squared. And I know you're saying 36 minus 9 is not really, rocket science, right? We could figure that back in elementary school before we knew about X's and Y's. But we're going to use this to prove that difference of squares works exactly the way that we want to see it. So x squared minus y squared. So let's substitute the 6 and the 3, because this is 6 squared minus 3 squared. So 6 and 3 are substituted in. On the other side, you got x minus y times x plus y. So we're going to substitute the 6 and 3 in for x and y there as well. So if we take x squared minus y squared equals x minus y, x plus y, and we substitute our 6 and 3, we got 6 squared minus 3 squared equals 6 minus 3 times 6 plus 3. So if we simplify this, 6 minus 3 is just 3. 6 plus 3 is 9. And then we have 3 times 9 is 27. So 6 squared minus 3 squared equals 27, which is the same as the 36 minus 9. 36 minus 9 is 27. So we prove that the difference of squares works by substituting numbers in and looking at it numerically. Seeing that gives us a lot of confidence that we can use this shortcut. Professor McMurlock says it's always good when the clues lead exactly where you think they should. This is not suggesting a completely new way of doing arithmetic. It's just a manner of proving that these polynomial identities apply to numbers as well there. So some of the identities can be applied to generate special numerical relationships. Let's look at the second example. 9 to the third plus 5 to the third power. So this is the sum of cubes, right? These are both being raised to the third power. So we have to select the appropriate identity, sum of cubes. A sum of cubes could also be used on an expression like 27 plus 1, since 27 is 3 cubed and 1 is 1 to the third power. So we can do that. So now let's apply that. So that identity says x plus 3 to the third equals x plus y times x squared minus xy plus y squared. So if we substitute our 9 and 5 in, because that's what it gave us, 9 to the third plus 5 to the third. 9 to the third plus 5 to the third equals 9 plus 5. We're just substituting 9 everywhere there's an x, substituting 5 everywhere there's a y. 9 plus 5 equals 9 squared minus 9 times 5 plus 5 squared. So now we just simplify all of this and do the math. 9 plus 5, that's going to simplify to 14 by the time we get down here. 9 squared is 81. 9 times 5 is 45, and 5 squared is 25. So we've got 81 minus 45 plus 25, and that all simplifies to be 61. Then we multiply 14 times 61, and we end up with 854. Now, if we're wanting to prove that works, we might want to open up our calculator just to verify that 9 to the third plus 5 to the third does equal 854. So let's take 9 to the third power here. Let's do it the old-fashioned way. 9 times 9 times 9, right? That's 9 to the third power. So that's 729. All right, now let's check 5 to the third power. 5 times 5 times 5, that's 125. So if we add that to the 729 that we just calculated, it indeed is 854, which is what we found using the sum of cubes. So numerically, that works. And a lot of times when I've been trying to figure out equations, I'll substitute numbers in just to see if it holds true, because that tells me if I got this equation right. Because we know it should work with numbers. Substitute in for all the variables. Let's look at the Pythagorean theorem. So any numbers that actually work for the Pythagorean theorem, they have a special name. They're called Pythagorean triples. Pythagorean triples. So famous ones are 3, 4, 5. 3, 4, 5 is a famous Pythagorean triple because 3 squared plus 4 squared equals 5 squared. Or 5, 12, 13 is another common one. 5 squared plus 12 squared equals 13 squared. But through the application of identity, Pythagorean triples can be generated. So here's a 4-variable polynomial identity called the 2-square identity. We haven't looked at this one, but they're giving it to us right here. A squared plus b squared times x squared plus y squared equals ax minus by squared plus bx plus ay squared. Wow. So for the purpose of this lesson, this identity will be used with 2 variables instead of 4. So we're going to substitute x and y for a and b and then simplify it. Okay, so if we substitute x and y for a and b, it looks like this. X squared plus y squared times x squared plus y squared. So instead of having 4 variables, we've simplified it to 2 variables. So everywhere there was an a, we substitute x. Everywhere there's a b, we substitute y, which we have to do that on the other side as well. So it'll be x times x minus y times y squared. plus y times x plus x times y squared. So all of this simplifies down. If we got x squared plus y squared times x squared plus y squared, well, that's x squared plus y squared squared, right? Because we're multiplying the same thing times itself. Over here, if we simplify this, we can take xx minus yy squared, and that's x squared minus y squared squared. And over here, we've still got the yx plus xy squared. We can rearrange that to be x times y, because y times x or x times y is the same thing. You can take 2 times 4 or 4 times 2. It's the exact same thing. So we can change this to xy plus xy. And then that's 2xy squared. So let's look at that last line. Notice it has one quantity squared is equal to the squares of the other two quantities squared. And then added together. So x squared plus y squared squared is the same as x squared minus y squared squared plus 2 times xy squared. It says that's the Pythagorean theorem. What? Assume x is 3 and y is 2. Show me how this is the Pythagorean theorem. Well, if we have x is 3 and y is 2, you got 3 squared plus 2 squared squared. And then 3 squared minus 2 squared squared plus 2 times 3 times 2 squared. So 3 squared is 9, 2 squared is 4, 3 squared 9, 2 squared 4. 2 times 3 is 6, times 2 is 12. And when we simplify all this, 9 plus 4 is 13. 9 minus 4 is 5, and 12 squared. So 5 squared plus 12 squared equals 13 squared. That's a Pythagorean triple. 5, 12, and 13. This is the Pythagorean theorem. A squared plus b squared equals c squared. That is one of the famous Pythagorean triples. But we would have never thought of it like this. That's just crazy. So this is the same thing in a whole different way. Math mysteries right there. This was a more involved proof, but all the clues along the way were algebraic skills we already knew. We knew how to simplify and combine similar terms like that. Let's look at page 3. Professor Sherlock McMurlock, likes the difference of squares identity because it wraps up so cleanly. He wonders, can we take this to a higher degree? And you're like, hey, McMurlock, get back to your pizza thing. Quit pushing us to higher degrees. Now we can do this. So McMurlock knows that x minus y times x plus y is x squared minus y squared. But what about x squared minus y squared equals x squared plus y squared? So take each of these and square each of those terms. How does that work? Does it end up anything related to this? Is it similar? So if we take this, x squared minus y squared and x squared plus y squared, and use the distributive property, you got x squared times x squared, which is x to the 4th. Then you got x squared times y squared, which is x squared y squared, minus, now you got y squared times x squared. So that's another x squared y squared. And then y squared times negative y squared times positive y squared is negative y to the 4th. These middle terms cancel out. One's positive, one's negative. They're exactly the same. So it ends up x to the 4th minus y to the 4th. Oh my goodness. It's exactly like this, but you can change it to x minus y as both squared and x squared plus y squared, and these become to the 4th. X to the 4th minus y to the 4th equals x squared minus y squared, x squared plus y squared. So being a good mathematician, old Sherlock McMurlock knows you should test this with some actual numbers to prove it's true. So if we say x is 4 and y is 1, let's see how it works. 4 to the 4th power minus 1 to the 4th power should equal 4 squared minus 1 squared times 4 squared plus 1 squared. So 4 squared is 256. And we subtract 1 because 1 to the 4th power, 4 to the 4th power is 256. 1 to the 4th power is 1. 4 squared is 16. 1 squared is 1. So we got 16 minus 1 and 16 plus 1. 256 minus 1 is 255. Over here, we've got 15 times 17. And 15 times 17 is 255. So even though it looked like it worked up here with all the algebra, it does when we use actual numbers. That is pretty cool to come up with a new identity just multiplying these together. Finding your own identities will not always work out into nice, clean, tidy expressions. This one worked. If you tried it with other things, maybe it'll work, maybe it won't. I think of the Pythagorean theorem. If you got a squared plus b squared equals c squared, what about a to the third times b to the third? Does that equal c to the third? You can test it. That doesn't mean they're not valid. It's important to check it with numbers like this, even if it doesn't come out right. Sometimes it works if you put numbers in it and say, oh, it really does work. Here's the lesson summary. So, algebraic proofs. Polynomial identities can be proven to be true by simplifying the identity to applications of algebraic theorems and principles. Start with the side of the identity that can be simplified the easiest and see if it ends up the other way when you go through all the algebra. Sometimes following a clue will lead to a dead end. It's like, oh, that didn't work. So don't follow up, just follow a different clue. The more practice you have with proofs, the more you'll be able to predict dead ends earlier. And then application numerical relationships, replacing the variables with numbers can help prove numerical relationships as well. So polynomial identities and polynomial proofs. This is what you use to prove new theorems in math as they start applying algebra to it. All right, drag the polynomial identity to the numerical relationship it will prove is true. So 121 minus 16 equals 105. 121 is 11 squared. 16 is 4 squared. So that looks like a difference, since it's subtracting, difference of squares. And it is. 14 squared equals 10 plus 4 squared. Well, this is a binomial, and we're squaring it, the square of a binomial. 64 minus 125 equals negative 61. 64 is 4 to the third power, or 8 squared. So we can go either way right now. This is either a square or it's also a triple. 125 is not a square, though. There's not a number you can square and make 125. So this is 5 to the third power, because 5 times 5 times 5. So these are both cubes. So this is a difference of cubes. And then we have 8 plus 1. Well, 8 is 2 to the third power. 1 is 1 to every power, 1 to the third power. So this is adding 2 cubes together. Fabulous. All right. Prove that the difference of cubes is true. So use some numbers or start solving which side you want to solve. Like multiply those together. Use the distributive property. Use polynomial identities to prove 63 squared equals 60 plus 3 squared. Check your work. So that's the square of a binomial theorem. And there's more problems there. Prove 3 squared plus 7, or 3 to the third plus 7 to the third. Which polynomial, apply the polynomial identities that prove that 99 equals 100 minus 1. Difference of squares, because that's 10 squared and 1 squared. All right, very nice. Last page. Assessment. Oh, look at this. This got an assignment down here. You're going to decide an advertisement for a new political identity that you're going to invent. You're going to create your own. Your goal for this activity is to demonstrate the proof of your identity through an algebraic proof and a numeric proof in some engaging way. Make it so the whole world wants to buy your new identity and can't imagine living without it. So you're going to make a flyer or a newspaper or a magazine advertisement or make an infomercial, or a radio commercial, audio recording, or design a visual presentation through a flow chart or PowerPoint. So you got to label and display whatever your new identity is, prove that it's true, and demonstrate that it works on numbers. Warning, no identities that we looked at in this lesson can be used. You got to create your own using the columns below. You can combine any of these type of things. See what happens when different binomials or trinomials are combined. You know, square a factor of this and add it to a factor of this to get your own identity. So when you get over here, oh, let's go back and look at this. Polynomial identities and proofs. So this is where the assignment is. You just have a submission page. There's nothing there, no questions, because it's time to show off your creativity and marketing skills. So that's the lesson. The other thing we have here, 4.07, solving polynomials, discussion-based assessment. So this is the other thing we have this week. We're going to have signups for our discussion-based assessment, where I will ask you questions based on what we've been learning on polynomials. I'll ask you questions. Oh, here's the grading rubric. You know, did you apply? Can you apply what you learned? Do you know the content? Are you accountable? You know, how are your 21st century skills? Do you engage in the discussion, basically? And there's, again, nothing. You could just put here when you did it. I did it on 12/11 at noon. Yeah, or whenever you turned in your assignment or did the discussion-based assessment. And that's all we have. Let's see, under the review and practice test, there is no practice test for this unit, but it will review what we've looked at. Polynomial long division. This is like the lesson summary for each of those. So if you're looking for a review before the discussion-based assessment, you can go and look at all of the lesson summaries. Oh, that one's not opening up. Try it again. Theorems of algebra. Yeah, you can look at all the lesson summaries from each of the lessons that we've done. So that's right there. The only other thing we have down here is the final semester exam, which you can open, but you can't do it until you get the password from me. So I have it password protected. I'll give you the password when we take the final on Wednesday, December 18th. That's when I'll give you the password. We'll come to class. I'll give you the password. Then you can go take the final, but no final until finals day. So we really just had one lesson today, right? And it was over these proofs. And you're looking at this and going, oh my goodness. So I got to make up my own identity and do a whole presentation or video or radio commercial. All right. Well, here's where I'm going to give you a Christmas present. I'm going to make that assignment optional.
Oh, yeah!
If you need to boost your grade a little bit and want to do that assignment and you do well on that, you can boost your grade a little bit. If you turn in a nice presentation, you know, you can get those points. It'll boost your grade. If you decide, I'm happy with my grade, I don't need to do that, I'll just put an X on it like it was never even assigned. It won't count against you. It just won't count, period. 4.05, the polynomial identities and proofs, the one that you have to make a presentation for. That's going to be optional. That's your Christmas present. Let's look on the discussion-based assessment. We'll talk about that, though, because everyone needs to do that this week. I'm going to put that up here on the screen. Going to our Google Classroom, that's where you need to go look at. In our Google Classroom, if you go to the classwork tab, okay, let's go to the classwork tab and look at week 17. That's where we're at. If you click on Do This Week in Buzz, when it opens up, here's a sign up. Discussion-based assessment. Sign up for, oh, I don't know what it's doing now. Sign up for a time below. If I click on this, I have times available Wednesday, Thursday, and Friday. Now I'll show you this. These times run from 10:40 till 11:45. You can sign up for a time. Or, like here's Thursday, same times. You can just come to class. You can sign up for a slot there. You can sign up for a slot. I got like 12 slots during class. It shouldn't take but about 5 minutes. So you can, because this is a B day Friday. So we have class. I'm sorry, on Wednesday. Your class is third period. This is a B day, so we only have class on Wednesday, but you have these other times on Thursdays and Fridays. If you want to sign up for basically sixth period, right? Sixth period, 10:40 to 11:45. This is my other algebra class that signs up for fifth hour. But there's lots of slots on Wednesday, Thursday, and Friday, in addition to our class time. So find a time for you to sign up so you can get this done. You'll meet with me. If there's more people in the class, I'll do a breakout room where it's just the two of us. So you're only answering questions with just me. And I'll ask you about what we've been studying. And then you'll get a grade based on your ability to answer those questions, right? The knowledge that you display when I ask you questions. So that's what we got this week, guys. You've got the rest of this class period. If you want to, if someone wants to hang around and do the discussion-based assessment now, I'm fine with that. Or if you need to catch up on some work, some of you have some work that you're behind on. So I will accept late work up until the final next week. Once I get the final, I got to get all the finals graded. I get grades in for the semester. So up until Wednesday next week, you can still turn in late work. All right, I'll take any late work you got up until Wednesday. When we have the final, it's closed. That's it. So whatever you got that you're missing, spend some time over the next 9 days getting all of that turned in that you can. Because I'll repeat what I say every year. I've taught virtual for many years now, and the only students I've ever had fail, and I have students fail every semester, the only ones that ever fail, though, are the ones that have missing work. Generally, if you turn in all your work, you know enough to at least raise your grade to passing. You've learned that much. It's all the zeros that pull your grade down. But if you turn it in most of the time, well, so far every time, I haven't had anyone fail yet that's got everything turned in. But get things caught up. And remember this too, if you take an assignment and you do it, one of these 5-question quizzes, and you make a 20% on it, retake it. It lets you take it multiple times. It'll only let you take tests one time. But all these other assignments, you have multiple attempts. And if you do poorly on a test, you can always email me, Mr. Ruck, can I retake this test? Now, I may send you a question to answer first. Hey, can you tell me what the answer to this is? I made something just so you've looked at what you missed. But yes, I can reset and reopen tests, and I allow retakes. So you get 20% on something or 0% on something. Don't settle for that. Go back and look at what you missed. Go back and say, why did I miss that? Go back and look at the lesson if you need to. Go back and look at my class video if you need to. Whatever you need to do to figure out, why did I miss that? Oh, I'm doing this totally wrong. Now I understand. Let me retake it. Yep. See, now I got an 80% or 100%. So don't give up when you get a 20% on something. Go look at what you missed. Figure out how to do it right. You can do that. So, all right, guys. I'll give you the rest of the class period for yourself to work on whatever. And we will have class on Monday. The finals on Wednesday, but we will have class on Monday. I will not have a new assignment for you on Monday. We're not going to throw something on you on finals week. That's not happening, but we will meet on Monday. So if you need to be here Wednesday, this is a B day Friday, like I said. If you need to be here Wednesday, I will see you Wednesday. Otherwise, I'll see you Monday. But if you want to hang around and work in here, I'll be here for any questions you got, and I'll be able to help you with whatever. So have a great week, guys. Christmas is almost here.